So let's just do a quick run through about calculating some capacitor energy and see what happens for a simple circuit. So first we're going to start off with 120 voltage or 120 volts potential drop across an initial capacitor C1 of 8 microfarads. And what we're interested in is, well, how much charge is initially on this guy. Charge is going to be equal to capacitance times voltage, and the capacitance is simply going to be 8 microfarads. The voltage is going to be 120 volts, and so we're looking at a grand total of 960 microcoulombs across this guy. How much energy does this guy store? Well, that's just going to be 1/2 times the initial charge multiplied by the initial voltage. So really 1/2 times 960 times 10 to the minus 6, and then 120. And so my initial energy is going to be 0.058 joules. Then kind of what happens is we take away that 120 volt potential source and we hook this capacitor up to the other capacitor, kind of throwing this switch right here. Now what's going to happen is this charge is going to flow. At the end of the day, the charge on this initial plate is going to go to both of those plates, but charge must be conserved. So now we kind of have two capacitors that are hooked together in parallel, and so we can write the equivalent capacitance of these guys simply to be the algebraic sum of these guys. Here we have capacitor 2, C1 plus C2, so 8 plus 4 is going to be equal to 12 microfarads. And I can kind of draw an equivalent capacitor that's going to look like this. Now I have my 12 microfarads, and I'm going to have Q1 plus Q2. I'm going to have 960 microcoulombs across that. What that means is I can write that the voltage is going to be equal to the total charge divided by the equivalent capacitance. So that's going to be 960 divided by 12, and my potential is going to be 80 volts. What I can then do is I can work my way backwards and say this same 80 volts is going to be across this capacitor, same 80 volts is going to be across this capacitor, and I can figure out what the charges must be along these two capacitors simply by using that the capacitance is equal to the charge divided by the voltage. Now everything that we've talked about up to this point about capacitors has assumed that there is a vacuum between the two plates that we have here, and we know in the real world we're not going to have vacuums. We're not going to have vacuums in electrical components. It's just too hard to maintain. So what we do is we insert a non-conducting material that just has a special name called a dielectric, and we stick that between the two plates. What this is going to do is it's going to change the capacitance. It's going to increase the capacitance, and it's also going to increase the energy density. How much is it going to change it? Well, it's going to depend on the dielectric constant of the material. This dielectric constant has a symbol K, and what it's going to do is it's going to be the ratio of the new capacitance right here to the capacitance in a vacuum, and this number will always be greater than 1. It's going to always increase the capacitance, increase the energy density. You can kind of see in this diagram, this is what real capacitors are actually going to look like. Think of it as just a big long roll of two conductors separated by a dielectric plastic sheet, and we roll it up to get as much surface area as we possibly can, to get as much capacitance as we possibly can. Of course, the non-conducting material, the dielectric, is going to have some charge separation on it. It is not a conductor, and so it's going to get some induced charges on it. Just a table of some dielectric constants. You can see if K is equal to 1, that's just going to be a vacuum. There's going to be no change in capacitance, no change in energy storage. Here we have air, very similar to a vacuum. Teflon is going to double it. Mylar is going to triple the capacitance, and so on and so forth, just looking at different materials. So what's going to happen is if we have a capacitor and we insert a dielectric into it, it's going to have some positive charge on this plate, it's going to have some negative charge on this plate. I've told you that the capacitance is going to be changed, it's going to be increased, and what must happen is the charge is going to be conserved, so the charge cannot change. What's going to happen then is the voltage must decrease. So here we have an example. I'm following 24.10. I've saved you the first step of calculating the initial capacitance, and what it says is, we have some capacitor without the dielectric. It had some capacitance, and we measured a potential drop of 3,000 volts. We insert the dielectric, so now we've gone ahead and we've inserted that dielectric right there, and we've discovered that the voltage has dropped to 1,000 volts. So what's the dielectric constant and what is the capacitance? Well, first let's go ahead and let's calculate what the charge is. The charge is going to be equal to the initial capacitance multiplied by the initial voltage, which is going to be 177 times 10 to the minus 12th. That's a picofarad right there. And then the voltage is going to be 3,000 volts. And we're going to get 5.3 times 10 to the minus 7 coulombs. That's going to be the charge. And again, the charge must be constant before and after you insert the dielectric. Charge will be conserved. What we can then say is this new capacitance is going to be equal to the charge divided by this new voltage that we measured. And so we're going to have our 5.3 times 10 to the negative 7th. Divide that guy by the new voltage. We're going to get 1,000 volts. And we can calculate out our new capacitance to be 5.31 times 10 to the negative 10th farads, or that's going to be 531 picofarads. So you can see that the capacitance has indeed increased. Now it's a simple matter of saying that this dielectric constant is going to be equal to the new capacitance divided by the original capacitance. So 531 divided by 177, and I've just left off the times 10 to the negative 12 because it'll cancel out, and we can see that the dielectric constant is going to be equal to, so we know that the capacitance is going to be increased. Let's talk now about the energy. Well, we can write the initial energy stored in this capacitor to be 1/2 multiplied by the charge multiplied by the initial voltage, and then we can also write the energy is going to be equal to 1/2 the charge multiplied by the final voltage. And we can see that charge is going to be the same. Voltage is going to go from 3,000 volts to 1,000 volts, and so we can convince ourselves that the energy stored in this capacitor is going to decrease by 3. Now let's take a look at the initial electric field. Initial electric field is going to be equal to the voltage divided by the distance of separation. The final electric field is going to be equal to the voltage divided by the distance of separation. Keep in mind this is the original voltage. The distance of separation here is going to be 10 to the minus 2 meters. So that's not going to change. The voltage is going to go from 3,000 volts to 1,000 volts. So what's going on here is it's also decreasing the electric field by a factor of 3. So the electric field is going to decrease by a factor of 3. Well, I'll just write 1/3 here. So that's what's going to happen to the electric field when we insert a dielectric. That's what's going to happen to the energy in a dielectric, and that's kind of how we can calculate capacitance using, or how we can calculate the dielectric constant by looking at how much the voltage changes. Kind of a heuristic diagram of what we just showed using equations is here we have a capacitor with no dielectric in there. It's going to have some initial electric field. It's going to go from positive to negative. We go ahead, we just insert the dielectric, and what's going to happen is it's going to have some charge separation to it. We have an insulator, so the charges cannot flow, but they can separate. And so what we're going to do is we're going to start inducing negative charges in the dielectric over here, and we're going to have positive charges in the dielectric here, and that's going to create a weak electric field inside of the insulator. It's going to essentially be canceling out some of the electric field, and the resultant electric field at the end of the day is just going to be a little bit weaker. Now, dielectrics can break down. They can break down if the electric field is strong enough. It has a special name called dielectric breakdown. How can you get the electric field strong enough? You crank up the voltage on this guy. And so really what we can do is we can look at different materials, and we can say, okay, these materials are going to have some dielectric constants, and this is going to be the point where the dielectric is going to break down. And if you take a look at capacitors, it's going to have some voltage rating. What that's really saying is we know what the distance of separation is. Don't exceed this voltage, because that's going to create an electric field that's going to cause the dielectric inside of this capacitor to break down. Note that when a dielectric breaks down, it becomes a conductor, so really not a very good thing for electronics.